Welcome viewers back to this course. So today we are going to discuss the lecture 9. So today we are going to start with a new topic, and that is called Green's function. So this Green function is basically used to find out the particular solution of any second order or any linear differential equation. So as we have been doing this course, so in the last class also we have started with second order differential equation. So L is my differential operator, and this is the differential operator we have defined, d square y over dx square plus px dy by dx plus qx y equal to fx. So this equation, I know that this can also be written as L of y, because y is a function of x. So we can also write this equation as px y dash x plus qx y is equal to fx. So in this case we are taking the bounded domain. So x belongs to the interval that is AB, the closed interval, and we are assuming that the px and qx and fx all are continuous in the given domain. So now is this differential equation, I call it equation number 1. So this equation I can write as a Ly operating on a y is equal to fx, and if I want to solve this equation, I take the solution yx and I take L inverse fx, where this L inverse, because it is the, I know that the L is a differential operator, so this inverse will be the integral operator. So this integral operator is called Green's operator. So this is the inverse of the given differential operator. So now we are dealing with the linear second order linear second order differential equation. So this L inverse. So because if I am able to find this L inverse, then I can find the solution of this equation, and then we are able to solve the differential equation. Because so if you see this one, in this case I am solving this equation. So basically what I am going to do is that this my yx will be a particular solution. Because we are solving the differential equation that is a non-homogeneous equation, and for that we know that whatever the solution comes, that is called the particular solution. So in this case we already know the different methods when my function fx is some exponential function or a sine cos function or some other function, but we have solved this one when the given differential equation has the constant coefficients, and after solving the constant coefficient homogeneous equation, we are able to find the complementary solution, and based on the type of the function fx on the right hand side, we can apply the different methods to find out the particular solution. So that we have already done, and later on we also solve the equation using the variation of parameter. So in that case, if I know the two linearly independent solution of the corresponding homogeneous differential equation, then using that two solutions, that is y1 and y2, we are able to find out the particular solution with the help of variation of parameter. So the question comes that why we are going to start with this type of problem, this type of a new method. So, in this case this method Green's function is useful, because we know that if I take the equation number 1, my differential operator is fixed, and if I treat this equation as a initial value problem or the boundary value problem, so in that case also the initial condition are fixed or the boundary condition are fixed. But what about if I change the right hand side? My right hand side function I change. So, if I go by the previous methods, then every time the function f(x) is changed, I have to change the strategy to find out the particular solution. So, just to get rid of that one, we want to apply the method that is called the Green's function. So, now, so my solution is yx. So, this operator actually we define like this one. So, that is defined as g and some, so I call it g the function of x and xi, and then f of xi d xi, and xi is belonging from a to b. So, if I do this one, this is the L inverse and operating on the function f(x). So, we call it the f xi because this is the indexing we are taking. So, in this case this is the solution of the given differential equation 1, and in this case the kernel, because this is gx is called the kernel, and this kernel is called Green's function. So, the main thing is that to find out these green functions for the given linear differential operator. So, before that one, so we want to introduce another type of function, that is we call it the spatial function to deal with such problem. So, that is called so I define a function that is useful for developing the theory of the Green's function, and that is called step function, or this is also called Heaviside step function. So, what is that? So, we define a function, we call it h x minus a, where x is my variable and a is some fixed value. So, I call it that this function has value 0 when x minus a will be less than 0, and from here I can say that when x is less than a, and otherwise its value will be 1 when x is greater than or equal to a. So, in this case if I want to plot this function, so this function is look like this one. So, suppose this is my a, x equal to a. So, if you see that this function is 0 for the whole value, so this is 0 function, and at x equal to a its value will be 1 and then its value will be 1 again. So, if you see this one, that this is the value 1 1. So, now in this case if you see, then this we have a value 0 and this value is 1, and here is a jump. So, it is also called the jump function, and we have a jump of width 1 in this case. So, this is called the Heaviside step function. So, this function has only two values, either 0 or 1. Now, so let us define another function with the help of the Heaviside function. So, let us see that I want to take the derivative of this function. So, I just want to calculate what will be the derivative of this function, d of h x minus a dx. So, this one I wanted to find. If you see that at x equal to a, it has the jump discontinuity. So, but if we take the x less than a, this is the function parallel to x axis, so its derivative will be 0. After this x equal to a greater than a, its value will be always, the derivative will be 0 because this is a parallel to x axis, and here we have a jump. So here if I want to find out the slope of this one, so that is infinity. So in this case this will be 0 when x is less than a, this will be infinity when x is equal to a, and this will be again 0 when x is greater than a. So with the help of this function, this value, we define a function, and then that is called Dirac delta function. This is called Dirac delta function. So this is by the physicist, that is the Dirac. So in this case we define a Dirac delta function. So I define a Dirac delta function delta x minus a, this is equal to, if I call it that is 0 when x is not equal to a, because if you say here x is less than a or x is greater than a, its value is 0, otherwise its value is infinity when x is equal to a. So from here I can say that Dirac delta also can be written as the derivative of d, the Heaviside function dx, and that can be written as a Dirac delta function. So this is the function, and this function has the property that for the Dirac delta, that if I take the integral from minus infinity to infinity of this function x minus a dx, then its integral is equal to 1. So if you just want to define this function, because this function if you want to draw, then you will see that, suppose I take this function, this is my function, and let a is equal to 0. So in this case this a is equal to 0, and so the function is 0 everywhere, this is 0, only at this point its value is unbounded, it is going very high, so it is unbounded. So this function has a 0 value everywhere except a, I have taken a equal to 0. So in this case the Dirac delta function will be delta x. So this is the function we can draw little bit about the Dirac delta function. Now the thing is that we want to prove this property. So for this one, because this is a special type of function, I define this function as a new function f, that is a x, and I define a new parameter epsilon. So I define this function as another function. So this function I take as, so this is I take a width, a interval of width, so minus, and this is x equal to 0. So in that I define a function, that this is a function whose width is, so this function I am defining, so this function, so my f x, in this case I take the width that is 1 over, so I define this function like this. Now it is just if I start taking the epsilon tends to 0, then this function tends to infinity. So in this case this is the width of the function, and that is the height of the function. So I define this function as this one. So I define the function f x is equal to 1 over, when my x belongs to minus pi to pi, and otherwise its value will be 0 when otherwise. So this is the function. Now if I take this function and I want to integrate this function from minus f x epsilon dx, then if you see this one, that the integral I want to define this function. So, this function is a positive function. So, basically I want to find the area of this function under this curve. So, from here I can say that minus epsilon to epsilon 1 over 2 epsilon dx, otherwise value is 0. So, this will be again 1 over 2 epsilon, and then this will be x. So, it will be 2 epsilon into 2 epsilon. So, its value will be 1, because in this case I have the width of that length 2 epsilon and the function is 1 over 2 epsilon. So, if I multiply, that value becomes a 1. The same thing I can apply for this function. Suppose I apply this one for minus infinity to infinity, from minus infinity to infinity dx. So, this one I want to define. So, if you see this function, I can write in this form, from minus infinity to minus epsilon f x epsilon dx plus minus epsilon to plus epsilon, and then from epsilon to infinity f x epsilon dx. So, in this case the value of this function is 0 from minus infinity to epsilon, this value is 0, this value is 0 here. So, from here I can say that this will be 0 plus minus epsilon from minus epsilon to epsilon f x epsilon dx plus 0, and this value we already know that this integral is 0 plus 1 plus 0. So, this will be 1. It means that if I integrate this function for the interval minus infinity to infinity, its value is also equal to 1. Similarly, I can do for a finite interval from a to b. So, in this case value the same way I can define, and its value will be again the 1. Now, if you see from the function I have defined, if I take the limit epsilon tends to 0 f of x epsilon. So, if I apply this limit, then you can see that if this width is going to decrease and becoming 0, then the height of the function is going to increase and going to become the infinity. So, if I put the limit epsilon tends to 0, this one, then I can say that when x is not equal to a, so in this case I have defined the function, this value. So, this value will be 0 when x is not equal to 0 and become infinity when x is equal to 0, because this function, if you see, so this is a function. So, when the epsilon tends to 0, we are heading toward the x equal to 0, its value will be infinity, otherwise value is 0. So, basically from here I can say that this is equal to a Dirac delta function. So, from here I can say that, so from here one thing is there, that the limit epsilon tends to 0 f of x epsilon is equal to Dirac delta function. So, this is the definition of the Dirac delta. Now, I want to define that what about, I know that from minus infinity to infinity my function f x epsilon dx, its value is equal to 1. So, just now we have done that one. So, now what I do, I take the limit. So, limit epsilon tends to 0 from minus infinity to infinity f of x epsilon dx, and this is equal to 1. So, by the Leibniz test I can take this interval this limit inside, and this will be so this one will be minus infinity to infinity, then the limit f x epsilon dx and that is 1, and I just now I have defined that this is equal to the delta function. So, from here I can say that is minus infinity to infinity, it is the delta function x dx that is equal to 1. So, this is what we want to prove. So, in this case I have taken the value a is equal to 0, and the same way I can define for the shift function. So, the same way I can define that minus infinity to infinity delta function minus a dx that is also equal to 1. So, with the help of this one, so this is we are able to prove. Now, the next thing I want to prove that is will be useful in future, that what about this one? If I take the interval from minus infinity to infinity x minus a, and then I define f x a dx. So, this will be what? In this case what we are doing, that we are taking the Dirac delta function and multiply by a function f x, and I want to see that what will be the value of this one. So, this one we will prove. Now, before that I just want to prove that taking the same function again that we have defined. So, in the last one I have defined, so just take, so I just want to write this as a g function. Now, I want to define that what will be the function f x epsilon into g x. So, this will be, if you see, this will be g x by 1 over 2 epsilon when x is from minus epsilon to epsilon, and this will be 0 otherwise, right. So, in this case, so this is my function, and so this is my x axis and this is the axis I am taking, y axis. Now, we have defined a function. So, this is minus epsilon and this is plus epsilon. So, in this case now I have defined another function. So, this function is g x over divided by 2 epsilon. So, this can be another function. So, in this case I just want to define that what is the area under this curve. So, I want to find out what will be the value if I take the integral from minus epsilon to epsilon f of x epsilon dx gx into dx. So, we know that this will be, so this function we have defined. So, this value will be gx over 2 epsilon dx. Now, the gx is a function. So, this function can be of this type, this can be of this type, but this is a continuous function in the given domain. So, it is an integral function. So, what do we do that I approximate this function, the height of this function by the value at this point. So, I can approximate this function as minus epsilon to plus epsilon, and I approximate this function as g at x equal to 0, because I have define the function, I am taking the interval about x equal to 0. So, I just take the value of the function as approximate value at x, g at x equal to 0 divided by 2 epsilon dx. So, from here I will get the value, and this is minus epsilon to epsilon 1 over 2 epsilon dx, and from here this value I already know that this is equal to 1. So, from here I can say that this will be equal to g of 0. So, f of x epsilon g x dx. So, this will be the value of the function here. Similarly, I can define this one for minus infinity to infinity f x epsilon g x dx. So, in this case also I can define this value as g0. Now, I just define the value of the Dirac delta function. So, I also know that if I put the limit epsilon tends to 0 for this integral gx dx. So, this will be again, so that becomes the Dirac delta function, that is x into gx dx, and this value is again, it will be equal to g0, because I have defined the Dirac delta function at 0. So, from here I can say that if I take the integral from minus infinity to infinity Dirac delta x minus a into gx dx. So, in this case this value will be equal to g. So, that is very one of the important integral or the properties of the green function. So, that is we are going to use a lot for defining the Green's function. Similarly, the same property I can define that from a to b over this finite interval, the Dirac delta and gx dx. So, that can be written as again the GA. So, this is for the finite domain. So, now after doing this one, so let us start that how we can define the Green function for the given linear differential operator. So, that the differential operator I know, so that is operating on the function yx. This yx is the function is a continuous, basically this belongs to C to AB, and that is giving me equal to fx. Now, I want to define that let L of I define the function g, that is the Green function, is equal to Dirac delta. So, this is the function I am defining, and this function is defining. So, let us define this operator, that operating on the Green function some g x epsilon, or epsilon instead of epsilon I can put the xi, because we are dealing with the xi here, and that is equal to I put x Dirac delta function x minus xi. So, now I know that this function can be written as, it would be 0 when x is not equal to xi, and this will be infinity when x equal to xi. So, in this case we know that if x is not equal to xi, then so if x is not equal to xi, then my v equal to 0. Now, if I have this one, and we have defined that with the help of the Green function I can define my, so this will be f x so this will be f of xi d xi. So that is the solution we have defined. So let us see what will happen here. I operate this one with the L. So L of yx will be L defining on this, operating on this interval in integral so I can take this operator inside with the help of Leibniz theorem. So from here I can write, so this will be L of g x I f xi d xi, because a and b are the constants, so other term will be 0, and this will be again a to b, and Lg we have just defined, that is equal to the Dirac delta function. So this will be x minus xi f xi d xi, and this one we have defined in the previous slide, then that this will be equal to f of x, because I am applying that delta x minus xi and we are taking the integral with respect to xi. In the previous one we are taking the here, so we are taking the integration with respect to x, like this one. So here we are taking the integration with respect to x and we will get the value Ga here. So the same thing is coming here. So in this case I am taking the integration with respect to xi, so I will get the fx. And what is this? So from here I will get that my L of yx is equal to fx, and that is the given differential equation we are solving. So from here one thing is clear, that if we start with this problem, that taking the Lg or operating on the green function, and that is equal to Dirac delta function. If I apply this one, then based on this one I am able to solve my differential operator or the differential equation. It means that if I am able to solve this equation, then I am able to solve with the help of green function, I am able to solve this equation, and from here I can find out the particular solution of the given equation. Now the main thing is that, now the question is that how to find, that is the Green's function for the given differential operator L. So that is our main goal, that how we can find the Green function for the given operator. So now you know that my operator L is d square over dx square plus px d by dx plus qx. So this one now what I do is that, if you see that L of applying on the Green function, that is equal to 0 basically when x is not equal to xi, because this is equal to Dirac delta function. So I just want to solve this equation. So this equation if I want to solve, I know that when x is not equal to xi, it will be 0, otherwise infinity. So I want to solve this equation for x is not equal to xi. So let us see what will happen. So if you see this one, so this is the equivalent to the corresponding homogeneous differential equation, and if I am able to solve this differential equation, then I know that from here I will, so this equation is equivalent to solving the corresponding homogeneous equation, and I know that this equation if I solve, then I can write the complementary solution of this equation if I am able to find two linearly independent solution, and I can write that the C1 y1x plus C2 y2x. So, this I am able to do this one. So, once we are able to find this value, so based on this one I can define my green function. So, in this case I just define my green function. So, this will be, I just define C1 y1x plus C2 y2x. So, this is because x is not equal to xi. So, in this case I am taking my x is lying between a and b. So, xi is also lying between a and b. So, this one I can say that this is when x is less than xi, and another one I take d1 y1x plus d2 y2x, and this is the case when x is greater than xi. Because x equal to xi, this will be infinity, so that we are not interested. So, this is the corresponding green function we are able to define. Now, the question is that I have C1, C2 and D1, D2, these are the four constants we need to find out to define the given green function. So, this one we can define with the help of the following properties of the green function. So, from here the properties we are going to use for find out this interval. The first property is, so this is the properties. The first one is that the green function g x xi is continuous at x equal to xi. So, in this case if this is a continuous at x equal to xi, so from here I can say that the C1 y1 xi plus C2 y2 xi is equal to d1 y1 xi plus d2 y2 xi, and from here I can say that C1 minus d1 y1 xi plus C2 minus d2 y2 xi, that is equal to 0. So, this is the first equation we are dealing with. So, this I call it equation number 2. So, this is the first property. The second property is that del g by del x has a jump discontinuity of magnitude 1 at x equal to x equal to xi. So, this is another property. So, if you see from here, I can define that del g over del x for x greater than xi minus del g by del x less than xi. So, this is defined at x equal to xi. So, this is equal to 1. So, from here we can say that d1 y1 dash xi plus d2 y2 dash xi minus c1 y1 xi c2 y2 dash xi, that is equal to 1. So, from here I can say that d1 minus c1 y1 xi plus d2 minus c2 y2 xi, that is equal to 1. So, this is another equation we are going to have. So, this is equation number 3. So, now you can see that I have equation number 2 and this is the equation number 3. So, we have two equations and we have four variables C1, C2, D1, D1, D2. So, that we have to find out. So, in this case I need two more equations to find out the value of all the C1, C2, D1, D2. So, that values basically, so those values or those conditions I needed. So, those conditions will come from, so those conditions will be coming from either the initial value problem, that is we have some y at x not equal to 0 and y dash y dash at x not equal to 0. So, this is the initial problem I am defining, or I will define the boundary value problem. So, boundary value problem I will define like y at x naught is equal to, so some value that I call it alpha, and y at some x1 that is beta. So, this also I can define, it need not be 0 always, it can be non-zero also. So, I just define this as a also alpha and this is equal to beta. So, this is my boundary value problem and this is my initial value problem. So, if I solving the initial value problem and try to find the green function for the initial value problem, then I will take the help of this one, and if I am solving the boundary value problem, then I will take the help of this one. So, based on this one we will able to get two more condition, and after having the four condition, that is equation number 2, equation number 3 and the two condition from here, we are able to find out all the value of C1, C2, D1, D2, and then we are able to define the green function for the given linear differential operator. So, now, so let us define, let us do one example of based on this one, because if you see, then the same thing we have done for with the help of variation of parameter also. So, in this case also I can find out. Now, from here, so from equation number 2 and 3, C1 minus D1, this is y1x. So, I just call it y1 because we have to write C2 minus D2 y2, that is equal to 0, and then I am defining this one. So, this is again I am defining, so that will be D1 minus C1 y1 dash plus D2 minus C2 y2 dash is equal to 1. So, from here I can define, so this one I just, because this value if you see, so this one I can write this function also like this one, just changing the position of, so I can write this as D1 minus C1 and D2 minus C2. So, now I have a two equation. Now, I know that, so from here I know that my y1x and y2x are linearly independent. So, if they are the linearly independent, then I know that the corresponding Wronskian, so this Wronskian we have defined. So, this one y1, y2, y1 dash and y2 dash, this will be not equal to 0. So, in this case if this is not equal to 0, then this will be linearly independent, and with the help of the Cramer's rule I can find the solution of this one. So, that solution if I find out, so this will be we have already done this one. So, d1 minus c1 I can define. So, this will be equal to minus y2 over the Wronskian at this one x equal to xi. So, this one I already know, and from here another equation if I want to write, then d2 minus c2 will be y1 xi over the Wronskian at x equal to xi. So, this is the value of the coefficients, value of the variable d1 minus c1 and d2 minus c2, that we already we have done for the when we will doing the variation of parameter. So, with the help of this one, now I can define now so from here, now in this case I can assume that this condition is either a initial problem or the boundary value problem. So, just in this case I assume that we are assuming that my C1 and C2 they are 0. So, let us we assume that one. So, in this case if I assuming this one, then I can say my d1 will be minus y2 xi over Wronskian and d2 will be y1 xi and that is Wronskian and this one. So, from here I can define my green function as xi. So, I have taken my C1 and C2 equal to 0, just I am taking this one. So, in that case this will be is equal to 0 when x is less than xi, and this will be equal to minus y2 xi y1 x plus y1 xi y2 x divided by the Wronskian when x is greater than xi. So, from here I can say that this will be equal to 0 when x is less than xi, and this will I can define as y1 xi y2 x minus y2 xi y1 x when x is greater than xi. So, this is my green function. So, in this case we can because I know that I am also solving this equation. So, this equation basically 0 when x is not equal to xi. So, this equation does not have a unique solution, because if I have g x xi is one of the solution, then g x xi plus y c, that is the complement solution, that is again the solution of this equation. So, this equation does not have a unique solution. So, in this case g x y, depending on that I have chosen in this case C1 and C2 equal to 0, I got this green function. If I have chosen C1 equal to 0 and D1 equal to 0, then this green function would have been the another one. If we choose C1 equal to 0 and D2 equal to 0, then we get the another green function. So, this green function is not the unique solution for this equation. So, in this case if we assume C1 and C2 equal to 0, then this is the corresponding green function for the given second order linear differential equation. So, in this class we have discussed that about the Heaviside step function, and then we have developed that what do you mean by the Dirac delta function. So, this Dirac delta function are very useful to define the green function, and then we have found that how we can find the green functions for the given a linear differential operator. So, in the next class we will go further and we will try to find out the green function for some various type of linear differential equation. Thank you very much. you.